Okay. Electronegativity, again, this is something we talked about last year, and bond polarity. So electronegativity, so this is just a table of electronegativity values, which are set to a standard for fluorine. Things to note, right, there is no noble gas column here because noble gases are excluded from the discussion, right? That's pretty much always one of those, trick multiple choice questions wherein you're given a noble gas and you think the trend is it increases going to the right, and then you pick the noble gas without thinking about it, right? So just, try to be mindful. Things to note, right? If you recall back to last year about hydrogen bonding, right? Hydrogen bonding only applies to N, O, and F, right? And that has to do with the fact that those are the highest electronegativities on the periodic table, right? Well, then you'd be looking and you might think to yourself, well, chlorine also has a very high electronegativity, but what's the difference between nitrogen and chlorine? Right, nitrogen is smaller than chlorine, yes? Nitrogen is smaller than chlorine. Other things to notice, right, are the carbon and hydrogen, right? Hydrogen is always going to be that weird one because it is so far away. The assumption is that its electronegativity is very different. But again, right, hydrogen's that one that there's nowhere else to put it that is better, right? The electronegativity of hydrogen is very similar to carbon, which is why we consider most hydrocarbon bonds to be nonpolar for the most part, right? And in terms of trends, right, as we go down, the electronegativity tends to decrease, right? As we go across, it tends to increase. All right, Lewis structures. So last year we talked about these as being our two double checks and being of the utmost importance, right? Because if you always double check those things, 9 times out of 10, you're going to get a Lewis structure right. It will be hard to get it wrong if you follow those double checks, okay? All right, so let's go ahead and practice a couple of things. Last year, we mostly stayed in the land of single central atom. This year, we are going to broaden the horizons a lot, right? So on average, the first element written is the central atom. But things to know, when we have carbons, right? Carbons will often be the central atom. If there's more than one carbon, the carbon makes up the backbone to which everything else is attached, right? So here, if we look, there is only one carbon, so we're going to put that carbon at the center, okay? And we'll see that there are 2 H's and there are 2 chlorines. Okay, well, and here is where we use our understanding of atomic principles, right? Hydrogen has 1 valence electron. It only needs 1 valence electron. It's only capable of forming 1 bond, right? So it's only ever capable of forming a single bond. Cl, we also, same principle, right? It only needs 1 valence electron. It's only going to form a single bond. And then we know that chlorines need to fill their valence, right? And then we would go and do our double checks, right? And carbon also needs 4 valence electrons, so it tends to form 4 bonds, right? So we already know all those basic things, which should help guide us to draw a really quick Lewis structure, which we can then double check, right? Hydrogen's octets are full. Carbon has 2, 4, 6, 8. It's full. Chlorine has 2, 4, 6, 8, 2, 4, 6, 8. When we double check our number of electrons, right? So we have 2, 4, 6, 8 plus 2, 4, 6, 8, 10, 12. So we have 20 total electrons. Does that make sense? Yes, that makes sense because we had 4 and we had 2 and we had, 14, right? So yes, that makes total sense. Good? All right. Next up, here we have C2H4. So we have 2 carbons. So again, carbons are going to make up the backbone to which everything else is attached. We have 4 hydrogens. Note that not all molecules are symmetrical, but if it's just a hydrocarbon, it's probably an okay place to start. Again, hydrogens will only ever have 1 bond, so we would start there. So we'd be like, oh, this is great. Let's see. Let's do our double checks. Okay. Do we have octets? Do these have octets? No. Something's wrong, right? So let's go ahead and count our valence electrons. Carbons have how many? Right, so this should be a total of 8 contribution. This should be 4. So there's 12 total electrons to distribute. 2, 4, 6, 8, 10, 12. Now, if we go back and evaluate, does everybody have a valence? Yes. Okay. All right, so then we're good here. Make sense? All right, last one. CH3COOH. So again, organic structures, right? So this actually is acetate, right? Whether you remember. There's 2 carbons, and again, carbons will form the backbone, right? To which everything else is attached. And in general, the formula is written such that the things are attached in the order they're written, right? So there are 3 hydrogens attached to that carbon, right? Which makes sense because carbons typically have how many bonds again? 4, right? So if we look here, this carbon now has 4 bonds, right? And then it says COOH, right? And so again, putting to use things that we know, right? We know that OH tends to be its own group. It's called a hydroxyl group, right? In organic compounds. But it tends to be its own group, right? So that means I have a CO and I have an O bonded to an H, okay? Now, here, let's just use our common sense things again, right? So oxygens tend to have how many bonds? Right, they tend to have 2 bonds because they need 2 electrons, right? So that tends to be the case. So if we look at our structure, is there somewhere that it seems like we're probably going to need to rectify such a thing? Right, here, this oxygen could probably use another bond, which works because that carbon needed another bond anyway, right? This oxygen, what might that one need? Right, like most oxygens, right, they tend to have 2 lone pairs, like this one, right? And then if we take a look in terms of octets, right, all the hydrogens are obviously good, the oxygens are good, the carbons are good. So let's go ahead and do a count on electrons, right? So we have 2 carbons, which is a total of 8. We have 4 hydrogens, and we have 2 oxygens, which would be 12, right? Which means we should have 24 total electrons. So if we count, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so this one's good. Make sense? Okay, so we have to have some way to validate Lewis structures if we are able to draw multiple versions that have the right total number of electrons and all the octets are full, right? So here we have an example for HCN, right? Where if we count our electrons, right, we have 1 plus 4 plus 5, so we have 10 electrons to distribute, right? So if we draw this, is H the central atom? Clearly not, right? So HCN, right? We know we're going to need some multiple bonds somewhere, so we could do that as one option, right? Likewise, if we were trying to be creative, we could just as well do this. And that would also mean we've distributed 10 electrons, right? So if we look, we have 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, right? That has 8, 8, 8, 8, 2, 2, right? So it meets all the criteria, right? You would be less likely to draw this particular structure because it says HCN, so you would assume that the bonding order should be HC and then N, right? But, you know, let's say you were just being creative and thoughtful, and it's the question to draw all plausible Lewis structures, so you did this, right? So then we have to have some other layer we can put on top that tells us which of these 2 Lewis structures is best, and that would be formal charge, right? Which is a comparison of how many electrons it brought to the table and how many it currently has access to, right? So what we're basically going to do is we're going to split the bonds and consider them equally shared, which is obviously not true, courtesy of electronegativity, but we have to have some way to do an approximation, right? So what this means is hydrogen has access to 1. It came with 1, which means its formal charge is 0, right? Carbon has access to 1, 2, 3, 4. It came with 4. Its formal charge is 0. Nitrogen came with 1, 2, 3, 4, 5, and it has access to 5. Its formal charge is 0, right? Here again, hydrogen 1, nitrogen has 1, 2, 3, 4, but it came with 5, which means plus 1. Carbon has 1, 2, 3, 4, 5, but it only came with 4, so minus 1. So obviously done right, if we use the right number, if we basically meet these criteria, then our formal charge should sum to 0 or whatever the charge is of the particular ion, right? And now that we have formal charge, we can say that this is the better structure because it has formal charges of 0, yes? Or like the rules in your book say, right, if there are only structures with if there is no structure with formal charges of zeros, we would want the negative formal charges on the most electronegative elements, right? Which is why this one is no good. Okay. All right, resonance, another layer that we can add to the Lewis model, right? There is a section from chapter 10 last year on resonance if you want like an easier wade into resonance to layer in with what's in your Brown and LeMay book. So anyway, ozone is one of those good examples, right? So your book talks about in ozone how one of the observations is that, so again, these are 3 oxygen atoms, right? Is that this bond length is equal, yes? The bond length is equal. Now, let's think about that, right? So a bond, if we think about it, right, means that we have positive nuclei, right, and we have electrons between them, right? And what it means when bond lengths are equal, it means that those bonds have to be the same, right? Because if we think about it, if there are more electrons on one side than the other, then this should be a shorter and stronger bond, right? That's what that means, right? More electrons shared between one pair of nuclei means a shorter, stronger bond than the other one, right? So if observational evidence said that there was one that was shorter and stronger and one that was a little bit longer and weaker, right? Then that would mean that ozone definitely looked like this, right? As in we had a double bond and a single bond, because that's what would fit, right? But observational evidence tells us that indeed those bonds are equal, right, in length and strength. If they are equal in length and strength, then there must be some other way to describe the bonding, which is what resonance gives us, right? So when we think about resonance, okay, I just doodled all over everything. Okay, anyway, so what that means then is that this picture is incomplete. So we would need to take this and then also say that that double bond could just as well be on the other side. And this would be a set of Lewis structures that better represent the ozone molecule, right? In that, again, in a resonance structure, the only things that move are the electrons, right? So it'd be like labeling this one as oxygen A, oxygen B, oxygen C, right? And this is still oxygen A, oxygen B, and oxygen C. So what it's saying basically is that some of these electrons can exist over here, or they can alternatively exist over here. And the actual picture is that they split time in both sections, so much so that we end up with what are equal bonds. Yes, does that make sense? Right? Which another way to say that, right, would be to say that one electron pair is delocalized. Yes, as in that extra pair of electrons is delocalized, right? Where localized means stuck to a place, right? Delocalized means not stuck to a place. So they actually can move throughout the molecule, right? Which gives us an essence of 1.5 as our bond length, strength, and or our bond order. Yes, instead of being 1 or 2, 1.5 is what we would call our bond order. Yes? Good? All right. So anytime a question says to draw all applicable Lewis structures, right, you should think resonance, right? Anytime something has a significant number of oxygens or sulfurs, right, we should think resonance structure. And again, right, we're not moving atoms. And if it's more visually clear to you, you are welcome to label your atoms like we did here, if that helps you to keep organized, right? Because this is not a flipped version, right? Because we could turn this molecule around, right, and say, oh, well, all we did was flip it over. But if all we did was flip it over, we would still have this scenario, right, where one bond is stronger than the other. Yes? Does that make sense? Okay. Next up, exceptions to the octet rule, because there are exceptions to everything, right? So for this one, last year, a lot of you guys were tempted to draw it this way, right? Which is perfectly fine and a normal thing to want to do based on the fact that everything should have an octet, right? Because here, we've met all the criteria, right? Everybody has an octet. But if this were the most accurate structure for boron trifluoride, what would be true? Right. One bond would have to be stronger and shorter than the rest of them. How could we rectify that? Right. We could say, oh, well, but perhaps there are resonance structures, right? And then you could draw a set of resonance structures, which would explain why that BF bond is equal in length and strength, right? There are 3 equal BF bonds equal in length and strength. But if you were given the additional observation that says boron trifluoride is extremely reactive, right, and will readily react with anything having a lone pair, that then tells you, right, that is your clue, right, that boron trifluoride is different, right? And the reason it's especially reactive is because boron doesn't have a full octet, right? So anything that happens to have a spare pair of electrons, like a lot of nitrogen compounds, right, will readily react with boron trifluoride, right, forming a bond with that molecule, right? But here, right, and that's the fun and beauty of chemistry, right, is that there are all these basic principles, right? But then we have actual experimental observations and we just need to figure out how all those fit together. Yeah? Okay. This is just that phosphate example that I allude to in the outline, right? Where thinking about what we're trying to do, right? One version might be a better explanation than another, just depending on what we're talking about. Yeah? Okay. Next up, bond enthalpies. This is the one topic that is definitely brand new for this year, but it's not very complicated, right? A couple of things to note. Obviously, if we're talking about multiple bonds, right, as we have, and if we think about a bond again, right, a bond is shared electrons between positive nuclei, right? So again, this is just a Coulomb's law discussion, right, where our charges are the positive nuclei and the shared electrons. If we have more shared electrons, Q goes up, right? Force of attraction is stronger, then the bond is shorter and thusly stronger, right? Okay, so you don't have to have any of these memorized in particular, just be able to use such a table. So moving along, right, if you are asked to determine the bond enthalpy of a particular reaction given a table of bond enthalpies, right, all you're going to do is you are just going to think about, here are my reactants. So first you need to know their Lewis structures. You're going to break all the bonds. This is not a terribly good picture, right? But we should break all the bonds. So this would be 4 CH bonds, and this would be 1 Cl bond, right? So we're going to break all of those, and then we're going to make all of these bonds, right? So we're going to make 1 CCl bond. We're going to make, oh, that's why they drew it that way. We're going to make 3 CH bonds, and we're going to make 1 HCl bond, right? So we would go find all of these, and we would add those up, and that would be a positive value. We would go find all of these, add those up, and that would be a negative value, and we would sum those two values together. Yes? Does it make sense? Note, again, like it says in your book and in your outline, right, that these are average values, right? These bond enthalpies are average bond enthalpies, right? So not every carbon bonded to a hydrogen requires 413 kilojoules per mole of energy input to break that bond, because it depends on what else that carbon is bonded to, it depends on what kind of medium it's in, depends on the temperature, depends on a lot of things, right? Which is why, for example, a calorimetry experiment or something else is always going to be a more accurate measure of bond energy, of a heat of reaction, as opposed to using these tables. But this gives us a good approximation. All right. Thank you for listening. Be good, and I will see you soon. Bye.